SwayamPrabha. Digital India. Educated India.
Let us look at example 2. This is model on infectious diseases. Total population region is initially 10,000 citizens, 10,000 area. New infections make citizens of susceptible population become part of infected population, which initially has just one person. Okay, so then it is getting closer to the existing model that we already seen. The number of infections is infection ratio and contracted susceptible population, infected population. Again, the model is quite straightforward there, and the values of contact rate is given, and infection rate value is also given, and the fraction infected equals infected population over sum of all other subpopulations. Let us see what are other subpopulations. Right now, it is only susceptible infected. If citizens from infected population die, they enter statistics of diseased population, else they recover. Okay, now it is interesting. Now we have diseased population and recovered population. So we have susceptible, infected, diseased and recovered. The recovering could be modeled as 1 minus fatality ratio into infected population divided by the recovery time. So how long it takes to recover affects that. Suppose average recovery time and average disease time, that is average time it take to die, are both 2.5 days. The fatality ratio is 90%. Only recovered infected population can spread disease to susceptible population. Okay. So that means once people die, they do not spread the disease. So assume they do not spread the disease further, so only the susceptible and infected population spread the disease, and even recovered also, recovered and infected spread the disease to the susceptible population. Okay. So let us look at what the model says and see whether we can spot the errors in the model. Let us open. One on disease population, so you can take it. Okay, so we have susceptible population, infected population, recovering population, disease population. Fine, susceptible. The flow seems to be make some logical sense. Infection moves them here, recovered moves them here and or here, either one of the places. The infection is given as a product of contact rate, infection ratio, susceptible population, infected fraction. So they are all seems to be connected there. Infected fraction is given as a relation between this and this. Infected population, total population, so that seems to be fine. Recovery dependent on infected population, time and fatality ratio, so that seems to be connected fine. Deaths also is given a similar relation, that seems to be fine. Let us quickly look at model settings. Final time 0.25 time step, week is time units is week, okay. And quickly look at the equations. Susceptible population is minus infection, which is fine because there is only outflow, there is no inflow here. So initial population, initial total population is minus infected, initial value. Initial total population is 10,000, which is fine. Initial infected is 1, that is fine. The equation for infected is infection minus recovery minus death, that is also fine, flows are fine. Recovering population, initial is 0, adds recovery, which is fine, only inflows are there. Disease population again 0, which is fine, and deaths plus, which is fine. Infection is just a product of all, which is fine. Value should be okay. Yeah. Recovery rate is 1 minus fatality ratio in infected population by recovery time, that was the description given, that is also fine. Deaths is infected and fatality ratio. So those who didn't die recovered, that is how it is modeled. So that's a 1 minus fatality ratio is there. Fatality ratio is given as 0.9, which is fine. Okay, recovery time was actually given as 2.5 days. So converted into weeks, so 2 by 7, 0.35 is fine. Contact rate is given as 20 per person per week, which is fine. Infection ratio is 0.75, which is fine, which is what was given. Okay, model seems generally okay. Let us run it. Okay, again I'm getting floating point error 3.75. The model seems structurally okay. Let us see. The recovery time was 0.35 per week, right? Okay. Let's go to model settings. Yeah, let's look at the time step. Here time step is 0.25. Or in our case, the smallest time step was 0.35 recovery time. Here it was 20 into 0.75. So here the time step the smallest was 0.35, while here the time step used is 0.25. So ideally we want time step be much lower than the smallest delay, right? So that could be a cause for unusual dynamics. We can actually look at the dynamics. Let us look at infected population. It is going negative. Large infected population or recovered population, everything just crashes and become negative. A susceptible population is increasing, which also doesn't make any sense. There is no inflows, yet it is increasing, right? So let us see whether time step is only issue here. Other seems okay. So instead of 0.25, let's go say 0.0315. Let us try that. Let us click OK. Let us run it. Okay, error stopped at least. Let us look at infected population. Okay, let me run it again. Okay. Just to let me get rid of the data set. I'm getting some other data set. Test 2 is loaded. So just delete the test 2. ID 001 is what we need to see. ID 001. Okay. Susceptible seems reasonable. I mean, infected seems reasonable. Susceptible has to decrease and went to 0. That's also reasonable. Recovering. Yeah, it's showing classical S-shaped growth. That's the dynamics we expect from this model. Disease population again shows S-shaped growth, but 9,000 people die and 1,000 people recover. That's because fatality ratio is 0.9. So that makes sense. Yeah. So this is the overall dynamics, and this is the only thing that seems to be error in this particular scenario. Okay. Questions in this case? So in this case, the main error was caused by incorrect simulation time step. So one way to check it is, let us create a ID 002. So in this case, I am going to change the simulation time step further down 0.0156, because we don't know what simulation time step to choose. Let us choose another time step to see whether there is any difference in the curves. So I reduce the time step further. Let us simulate again. Let us look at infected population. There is a difference. That means still we need to choose a more appropriate time step, such a way that we are getting a curve where it should not keep changing. Whenever there is a change occur, that means you have to keep reducing until you hit a time step where the change is almost nil. So let us do one more. Let us do an ID 3. Let us look at settings. Let us further reduce it to the smallest one possible, at least in Euler method. Let us run it. So ID3 shows the further small changes in the model. The first simulation time step to second, it was from point, what was it, from point 03 to 0.125, there was huge jump. There's further jump when we further reduce the time step. So in these kind of population dynamics, or rather the infectious disease model, we should remember that the origins of the model came from not from the system dynamics community, but came from the epidemics modeling community who use differential equations to model. So if you want higher accuracy to represent it better, then it's good idea to go for other integration types. So instead of Euler method, a more powerful integration tool would be a Runge-Kutta method. Those who have done methods on numerical methods will know that Runge-Kutta has higher accuracy. So let us just change it to RK4 and call it RK. Simulate it, let's see what happens. That gives us the most accurate results. This style seems to still improve based on the earlier ones. So in this particular case, we may want to prefer RK4 methods and check whether different time scales also makes a difference, else we'll go with the lowest time step where results doesn't change significantly. Let us look at the recovery population. So these are things we would like to observe in the sense where the steady state values is exactly the same, right. So steady state value is what we are interested in, it doesn't matter what we use, it all converges to the same 1000 as you can see right here, but the transient shape of the curve also doesn't change. So the actual dynamics doesn't change, but we are interested in highly more accurate results, the trajectory changes a bit. There is no large change deviations in the dynamics. When there is large deviation, then there is a major error in your logic. So you need to choose an appropriate time step. But once you get kind of similar results, then if you want more and more accurate results, it's better to have a smaller time step with a better method of integration. So the starting point is similar, ending point is similar, only the transient logic change. So we saw two things. First one was a small error in the flow equation, stock flow equation. Second one had a floating point error because of time step selection. Let us look at a third scenario and see what kind of errors it can have.